Section 11.3 is where we're going to cover Fisher projections, cyclization, and Haworth projections. So we're going to start out with Fisher projections. And what is a Fisher projection? Well, a Fisher projection is a method of depicting three-dimensional shapes for chiral molecules. And so what happened was Emil Fischer was characterizing or discovering all these new carbohydrate molecules. They had multiple chiral centers. For example, glucose has four chiral centers in it. And he was getting frustrated with drawing all the dashes and wedges. And so he wanted to come up with a faster way to represent these types of chiral molecules. And so instead of using dashes and wedges, he used an intersection of two lines to represent a chiral carbon. And so the molecule has a three-dimensional shape with horizontal bonds coming towards you and vertical bonds going away from you. So what that means is when we have a Fisher projection, and we have two bonds crossing each other like this, there's going to be a carbon in the middle. But what you have to understand is this is the same thing as this, where the bonds that are vertical are going back into the page. So there's my carbon. The one that's down is, or the one that's pointing up is going into the page. The one that's going down is into the page. And the ones that are horizontal are wedges. Those are coming out towards you, okay? So you can see how drawing just this cross like this, which represents this in three dimensions, is a lot easier to draw. And so that's the history of the Fisher projection. And generally speaking, when we draw a Fisher projection, we draw it so that the carbonyl, let's say we had an aldehyde, would be at the top, okay? And if you have a ketone, it would be at the top of the molecule as well. And so one of the simplest carbohydrates we can have that has an aldehyde in it is glyceraldehyde. It's represented with a small capital L when the hydroxyl group is on the left of the chiral carbon, and with a small capital D when the hydroxyl is on the right side of the chiral carbon when the molecule is oriented with the carbonyl. This says carboyl. It shouldn't say that. It's a mistake. It should say carbonyl at the top. And so you see L-glyceraldehyde and D-glyceraldehyde shown here. And these pictures here, these are Fisher projections, okay? So remember, it's like the horizontal bonds are drawn as are representing wedges and the vertical ones are dashes, okay? I'm gonna erase that. So when it says L, okay, L-glyceraldehyde, maybe I need a finer tipped pen here, but the L represents that the hydroxyl on this chiral carbon is pointing to the left, so pointing to the left, and the D here represents that the hydroxyl group here is pointing to the right, okay? And keep in mind, in order for this to be valid, that the aldehyde has to be at the top, okay? The aldehyde has to be at the top, otherwise the DNL designation is not valid. Okay, so lactic acid is a byproduct of ATP formation, and alanine is an amino acid. Draw Fisher projections for the DNL forms of the following. So we have lactic acid, we want to draw the DNL form, and then we have alanine, and we want to draw its DNL form. So we'll start with the lactic acid. This is the chiral carbon, this one right here, and there's a total of three carbons in the molecule. So what we'll do is we'll draw something like this and something like this. So there's no aldehyde in the molecule, but there is a carbonyl in a carboxylic acid. So we're going to put the carboxylic acid at the top. Now for the L form, the hydroxyl is going to want to be on the left-hand side. And so the hydrogen is going to be over here. And so the CH3 group would be down here. And so this would be L, lactic acid. All right, and if we want to draw the D form, all we have to do is draw the enantiomer. So we're just going to reverse the hydroxyl. So what I'm going to do to make this simple for myself is I'm just going to copy all of this. I'll just copy and I'll paste it over here. And then I'll alter the structure through the magic of the iPad. So I'm going to delete this and this and this. I'll put my hydroxyl on the right-hand side. And so there we go. Now I have my D-lactic acid. Okay, now for my alanine, here's my chiral carbon, It's similar to the last problem that there's a total of 3 carbons in the molecule. So for my alanine, I don't have an aldehyde, but I do have a carboxylic acid, and that has a carbonyl. I'll put that in the top. I'll put my CH3 group over here. And so for my L-alanine, I'll put my amino group on the left-hand side. And then for my D-alanine, I'll just copy and paste this, and I'll switch those. So I end up with my amino group over here. And so this would be my L-alanine, and this would be my D-alanine. Something that's interesting about these is that alanine, like it says here, is an amino acid, and lactic acid um, is a byproduct of ATP formation. But when it comes to sugars, sugars that are naturally occurring in our bodies are the D sugars, whereas the amino acids that are naturally occurring, generally speaking, are the L amino acids. And so what we have here on each side, again, just to reiterate, L-lactic acid and D-lactic acid, these would be enantiomers, okay? They're mirror images of each other. And over here, the L-alanine and the D-alanine, these would be enantiomers as well, non-superimposable mirror images. Now, like I said, Fisher developed the Fisher projection because he was getting sick and tired of drawing all these dashes and wedges on molecules that had multiple chiral centers. So what do we do in this kind of situation? So the existence of more than one chiral carbon in a carbohydrate molecule could lead to confusion when trying to assign D or L designation. So you can imagine we have a rule to avoid confusion. So to avoid this, we focus on the hydroxy group that is attached to the chiral carbon furthest from the carbonyl group. And you can see these are the ones that are highlighted in blue here on the right. So by convention, the D family of compounds are the ones where the hydroxy is going to be on the right, on the chiral carbon that is farthest from the carbonyl. And the L family, it's going to be on the left-hand side. So if we take a look, we've got erythrose and glucose molecules here. Now you can see the carbonyl group is at the top for every single one of them. But if you look at erythrose, right, erythrose, whether it's L-erythrose or D-erythrose, they both have 2 chiral carbons. Both of these carbons that I have highlighted in yellow are both chiral carbons. And both of these are chiral carbons as well. Now, if you're wondering about this carbon here, if you're like, well, that's the last carbon. Yeah, but that's not a chiral carbon. How do we know? Because that carbon is attached to 2 hydrogens, so it's not attached to 4 different groups. Whereas this carbon or this carbon is attached to 4 different groups. And let me prove it to you, 4 different groups, right? It's got a hydroxy, a hydrogen, a CH2OH, and then all of this. Those are 4 different groups. So since the hydroxy group on the chiral carbon furthest from the carbonyl is pointing to the left, this is L-erythrose, and its enantiomer, shown over here, is D-erythrose. And the same thing applies with our glucose molecules. I'll draw a little line here to divide them. So D-glucose is the one where the hydroxyl on the carbon furthest away from the from the carbonyl group rather, is pointing to the right, and then L-glucose is going to be the opposite. The hydroxy on the chiral carbon furthest from the carbonyl is pointing to the left. All right, so ribose is a component of ribonucleic acid RNA, which plays a central role in protein synthesis. Is the following ribose structure D or L? Well, if we take a look at our ribose molecule, we have our carbonyl, our aldehyde up at the top, and you can see this is the chiral carbon that's furthest from the carbonyl. The hydroxy is on the left-hand side, and so this must be the L structure, and so this would be L ribose. Now, if you have 2 enantiomers, right? Let's say you compare D versus L glucose. So D glucose versus L glucose. It turns out that those 2 enantiomers are going to have the same melting points, the same boiling points, the same densities, et cetera, et cetera. They're going to have all the same physical properties. And so how do we distinguish between enantiomers? It's very tricky, as a matter of fact. Well, the way that we distinguish between enantiomers is by the way they rotate what we call plane polarized light, okay? And so if you put one enantiomer in a solution and you shine plain polarized light through it. And if you're like, what is plain polarized light? Well, if we have unpolarized light, that's just like the kind of light you get from a light bulb. But then if you put it through a polarized lens like this, and if you have a pair of polarized sunglasses, they will have polarized lenses in them. And so you can see that in the unpolarized light, the light is coming out as a wave in all directions. But when we pass it through the polarizing lens, you can see it's only coming out of one direction. Okay, so it's only coming out of one direction here. And so here is a solution of our enantiomer, and then we shine the plane polarized light through it. And what's going to happen is that the molecule, if it's chiral, it's going to rotate the plane polarized light in one particular direction. And so if you're like, well, what's the big deal with that? Well, the idea is this, is that one enantiomer is going to rotate the plane polarized light in one direction. Let's say you had one sugar, and I don't have D or L glucose memorized, so I won't use them as an example. But let's say you had one D sugar and it rotated plane polarized light 10 degrees to the right. We say that's positive 10 degrees. Well, then that means that the L sugar is going to rotate it by the same amount, but in the opposite direction. So we would say negative 10 degrees. So if the molecule rotates plane polarized light to the left, we say it's levorotatory. And if it rotates it to the right, we say it's dextrorotatory. Now, one thing that might be a leap that students want to take, and maybe any scientist might want to take this leap, but they might think, oh, D and L sugars, D for dextrorotatory, L for levorotatory. However, D and L designations for the sugar, for the name, have nothing to do with how the molecule rotates plane polarized light. I repeat, they are not related whatsoever. So just because a molecule is a D sugar does not mean it's going to rotate plane polarized light to the right. It might rotate it to the right, it might rotate it to the left. The only way to know is to test it. And so when we talk about optically active molecules, we're talking about molecules that rotate plane polarized light. So again, this is one of the few ways that we have to distinguish between enantiomers. Okay, in this slide, we're going to introduce a couple of new functional groups, and you can see them here off to the right-hand side, a hemiacetal and an acetal. So it turns out that if you take an aldehyde, and we've seen a lot of aldehydes in this chapter, right? We've seen a bunch of them at the top of our sugars, okay? Aldehydes react with alcohols to form what we call a hemiacetal. Oops, hemiacetal, which is a functional group that's very important for carbohydrates. It turns out that hemiacetals usually aren't that stable, and under catalytic conditions, they're going to react to form a more stable product called an acetal. So the way you can think about a hemiacetal is you have a carbon atom, and it's like it has an ether on one side. So this is like an ether, and then it has like an alcohol on the other side. So it's not an ether and an alcohol, but it looks like an ether on one side and an alcohol on the other, and we call that a hemiacetal. If, on the other hand, you have a carbon that has an ether on one side and then an ether on the other side, right? Two ethers on the same carbon, that's what we call an acetal. Now, again, it's not a diether or anything. I'm just using that as a way to describe it. So hemiacetal, carbon with a hydroxyl and an OR group. Acetal, carbon with two OR groups would be more correct. So the general reaction for the formation of a hemiacetal is that we take an aldehyde, we treat it with an alcohol, um, and it's going to react. You can see it's in equilibrium here, but it's going to react to give us a hemiacetal. So you see, here's your carbon with an OR and with an OH. But it turns out it's going to react again with another molecule of this alcohol, and you're going to have your acetal, where you have a carbon with your OR and you not another OR, right? And the R groups, and I know you're all astute enough to notice this, but the R groups came from the alcohols, right? So here's a specific example. If we take acetaldehyde and react it with methanol, first we get the hemiacetal intermediate shown here. But then if we react it with a second molecule of methanol, you can see you have your carbon here, and it has an OR group here and another OR group here. And the R group is a methyl group that, right, that comes from methanol. So now you know acetals and hemiacetals. And so the reason why hemiacetals are so important for us in this chapter is because this is a chapter on what? Carbohydrates, right? And open chain carbohydrates, everything that we've seen so far, they both contain, or they contain both a carbonyl group and a hydroxyl group on different carbons. And so what can happen is what we call an intramolecular reaction or an intramolecular cyclization within the same molecule, which can result in the formation of a cyclic hemiacetal. So if you take a look at this sugar that's drawn here, okay, and what is shown here, it's the same thing as if you were to draw, your CHO at the top, right? This is carbon number one, then you have two, three, four, um, five, and six, like this. Okay, this is what they're drawing. So we have a hydroxyl here, one here, one here, and one here. Something like this, okay? So this is what I'm drawing in red is exactly what's shown here. But what they're showing is this oxygen. So this bond that they're showing being formed here comes from the reaction of this oxygen, so that's this one, with the carbon of the carbonyl, okay? And when it does, when I draw it like this, it doesn't look like anything, but when you see it drawn in this perspective, you can see how it forms this beautiful six-membered ring, right? So we have our six-membered ring, one, two, three, four, five, six, and we end up cyclizing to get beta D glucose in this case. And over here we cyclize and we get what's called alpha D glucose. So what's the difference between the two of them? Well, you notice that the only difference between these two is on carbon number one, isn't it? If I highlight carbon number one in green here and in green here, you notice that in the beta D glucose, the hydroxy group is pointing up in the perspective that we're seeing on the page. And then in alpha D glucose, the hydroxy is pointing down. And so when we have a cyclic hemiacetal, and again, you can see this is a hemiacetal because we have carbon, oxygen, hydrogen, and then oxygen, carbon. So that's our hemiacetal. Let me delete some of the spinach here. But anyhow, there's our cyclic hemiacetal. When the hydroxy group is pointing up, we call it beta. And when the hydroxy group is pointing down, we call it alpha. One of the ways you can remember this is if it's beta, right? You can turn a beta into a butterfly, right? And butterflies live up in the air. And the alpha kind of looks like a fish, right? And fish live under the water, right? Down. So maybe that's a mnemonic that you might find helpful. Also, carbon number one has a special name. It's called the anomeric carbon. And so there's my anomeric carbon. And so again, when we cyclize our sugar, we get a cyclic hemiacetal. I'll try one more time here. I'll circle carbon, oxygen, hydrogen, right? That's a hemiacetal. Carbon, oxygen, hydrogen. There's another hemiacetal. And if on carbon number one, the anomeric carbon, the hydroxyl is pointing up, we call that a beta anomer. Beta D glucose would result, as we see here. And if the hydroxy is pointing down, we get the alpha anomer, which in this case would be alpha D glucose. Now, the reason why we're so interested in these is that cyclic hemiacetals are actually much more stable than open chain compounds once you have more than five atoms in the ring. So you've heard me talk about the word anomer, right? I talked about the anomeric carbon, which was carbon number one, but I haven't brought up what a pyranose is. And a pyranose is a six-membered sugar ring system containing an oxygen atom. So whenever you have something that looks like this, where you have a six-membered ring, where you have oxygen in the back like this, that's a pyranose ring system. And so the Haworth projection, when we draw the six-membered ring in this manner, this is what we call a Haworth projection, where we draw groups pointing up and down and up and down, et cetera, whatever we're dealing with here. So that's a Haworth projection or Haworth structure. And the anomeric carbon, again, just some more information on that. The anomeric carbon is carbon number one, right? Anomeric carbon. An acetal, ketal, hemiacetal, hemiketal carbon atom that gives rise to two stereoisomers. And so ketal and hemiketal, those are just the analog of an acetal and a hemiacetal that you would get from a ketone instead of an aldehyde. And so anomers, right? Well, we see down here, we have beta and alpha D glucose. They are anomers of each other. They're just stereoisomers that differ in the three-dimensional arrangement of groups of at the carbon of an acetal ketal or hemiacetal or hemiketal group. And so, since the carbons that I have highlighted in yellow are the hemiacetal carbon, these two structures, beta D glucose and alpha D glucose, only differ here and here. You can inspect them all you want. The only difference is the beta hydroxy on the anomeric carbon of beta D glucose and the alpha hydroxy on the anomeric carbon of alpha D glucose. And so beta D glucose and alpha D glucose are not enantiomers, are they? They're not mirror images. They are anomers. They're stereoisomers, but they only differ in configuration at one carbon, and that is carbon number one, that we call the anomeric carbon. Now, what about a five-membered ring? Well, when we have a five-membered ring, we call that a furanose ring. And so whenever you see a ring drawn like this with an oxygen at the back, that's a furanose ring. And you can see one shown here in fructose. And I told you earlier that fructose and glucose join together to make sucrose, which is table sugar. So a furanose ring is a five-membered sugar ring system containing an oxygen, and again, you see the fructose down here. And you can see the difference between beta and alpha D fructose is at carbon number one, and I'll highlight it in yellow, the anomeric carbon. If the hydroxy is pointing up, it's beta, right? Like the butterfly. And if it's pointing down, it's alpha, like the fishy. So let's say you want to draw a Haworth structure. Let's say you're practicing at home and you want to draw some Haworth structures. Well, in drawing a Haworth structure of a monosaccharide, we follow these rules so that all the structures are represented consistently. And so this isn't just for our class, this would be for any class in chemistry. We draw our Haworth projections the same way, or Haworth structures the same way, so that we are consistent across the scientific community. So step one is going to be to draw the ring with its oxygen in the back. So you can see for the furanose here, we have our five-membered ring with the oxygen in the back. For a pyranose, we have a six-membered ring where the oxygen is in the back, but I'll just point out it's in the back right-hand side. In this case, I'll just put RHS for right-hand side. Step two, put the anomeric carbon on the right side of the ring. So anomeric carbon is going to be here on the right side of the ring. And the terminal CH2OH group, which is at position 6, should always be shown above the ring. So it should always be pointing up above the ring for a D monosaccharide, which is really all we're going to be interested in drawing in this class because they are the naturally occurring sugars. Remember that any groups attached to position 1, the anomeric carbon, can be drawn above or below the ring, depending on whether you're drawing the alpha or the beta. If it's alpha, it should be pointing down, and if it's beta, it should be pointing up. All right, D-galactose exists predominantly in the cyclic form. Given the following structure, draw the Haworth structure for the other anomer. Label the new compound as alpha or beta. So if we want to draw the anomer of D-galactose, we're going to copy everything except for the hydroxy group at carbon 1, the anomeric carbon. So let me just see if I can scribble this over here. So we'll draw our six-membered ring like this. We have our CH2OH group, which is above the ring. This hydroxy is pointing up. This hydroxy is pointing up. This one is down. Well, this one is alpha. So if we want to draw the anomer, we have to draw this one pointing up. And so this would be beta D galactose, right? All we had to do was reverse the hydroxy from down to up on the anomeric carbon, the one I have highlighted in green, and we went from alpha down to beta, pointing up.